Hi guys, my name is Emma. Today I'm going to be showing you a walkthrough of the Fall 2016 final exam. So let's get started. So the first question we look at, and we see each individual in a population belongs to one of two classes, a triangle or a square. Two attributes are going to be used to classify new individuals. The training set consisting of 12 points is shown on the right. Both of the attributes have been measured in standard units so that distances are comparable on the two axes. Okay, and part A is asking us to mark one new point, not in the training set, that a 3 nearest neighbor classifier using this training set would classify as a triangle. Okay, so we look and we see that the triangles in this set are here and here. And since we're going to be using a 3 nearest neighbor classifier, we want to put a point that will be near like the two triangles so that it'll be classified as a triangle, since that would be the majority if the 2 out of the 3 points were triangles. So we're going to put our new point right here, and that would be classified as a triangle. Okay, that's part A. And we look at part 2, and it says, this graph includes a new point not in the training set, shown as a star. Circle the 3 nearest neighbors in the training set of the star. Okay, so when we look at the star, the first nearest neighbor is here, the next one, is here and here. And so if we only had a one nearest neighbor classifier, we would classify it as a triangle because this is the closest neighbor. Okay? If we were using the 3 nearest neighbor classifier, we would look and see that 2 of the 3 points are squares, so we're going to classify that as a square. Alright, now we're going on to part C, which says, suppose the new point is below average in both attributes. In which class would it be placed by the 3 nearest neighbor classifier? Explain briefly. Okay, so when we look at this graph, we see that the average of both attributes is going to be at 0, which is right there and right there. So if a point is below average in both attributes, it's going to be like in this quadrant right here. And if we look at that quadrant, it's basically all squares. So if we had a point basically anywhere in this area, it's going to be classified as a square. So I'm not going to write out the entire explanation because it would take forever, but basically we would just classify it as a square. Okay, now we go to number 2, and we see this graph, which shows the after-tax income of census family units for Canada 2005 and 2010. Okay, and immediately we notice that there's something kind of weird going on here because it's kind of following this normal distribution that's kind of like sloping downward except for this one bar here. And the question is asking us to explain that. So the first thing that I did when I saw this question is I looked at each of the bar bins, basically, and I saw that the first 10 are going to be 9,999, but we're just going to call it 10,000 because that's easier. So this one's 10,000, this one's 10,000, etc. And then when we get to this 11th bar here, we see that it's going from 100,000 to 124,999. So that's almost 25,000. So that's obviously going to cause some issues, and that's why we see this really big difference in the heights of the bars. So we just have different bin sizes for the last 1, 2, 3, 4, 5 bins. And again, you'd probably want to give a little bit more explanation for this one, but that would just take me forever to write out, so we're going to skip over that. Okay, moving on to number 3, we are looking at a population of tiny birds. We're looking at the relationship between the diameter of the egg and the weight of the hatchling. And the correlation between these two variables is 0.75, and we have some statistics down here which are going to help us. Okay, so we are looking for the regression estimate of the weight of a bird that hatches from an egg of diameter 24 millimeters. So the egg diameter mean is 23 millimeters and the SD is 0.5. So if we think about it, 24 millimeters is going to be 2 SDs from the mean. Because it's 0.5 plus 0.5 equals 1, and 23 plus 1 equals 24. So now we're going to do the correlation times 2 SDs is going to give us 1.5 SDs, which is how far we are going to want our weight to be from the mean. So 1.5 times 0.4 will give us how far we want our weight to be from the mean in terms of these units. Okay, so that would be, we actually don't need to do the work here, so I'm just going to ignore that. And we're going to do 6 plus this number. That is how much, that is what you want the weight of the bird to be. So this is our answer right here. Okay. So we look at part B and it says, if you use the sample to make a bootstrap prediction interval at x equals 24 millimeters, the interval is for predicting the height of the blank. And the options are a regression line or the true line in the regression model at x equals 24. Pick one option and explain your choice. Okay, so if we think about it, we actually already have the equation for the regression line, so we don't need to be predicting that. What we are actually predicting is the true line in the regression model, because we already have the regression line and we're just looking for how close it is to the actual line. So in this case, we are looking for an estimate of the true line. And again, you would definitely want to add some more explanation, but that's okay. All right. Moving on to number 4. In this question, it says, a data science class has 500 students. As part of an assignment, each student tests the fairness of a coin using data from his or her own set of tosses of the coin. All 500 students test the same coin, and they all test the same pair of hypotheses. So the null hypothesis says the coin is fair, alternative says the coin is not fair. All the students use the same 5% cutoff of the p-value. You can assume that all the students perform the same test on the large number of tosses. Okay, so unknown to the students, the coin is fair, which means that the null hypothesis is true. Alright, about how many students will conclude that the coin is not fair? Pick an option and justify your choice. Alright, so if we think about it, the chance that when the null hypothesis is true, people are going to conclude that it's not true, is going to be the same as the p-value cutoff. So in this case, it is going to be 5% of the students conclude that the null hypothesis should be rejected, even though it is actually correct. So we want to find 5% of 500. Just do that math really quick. And you're going to get 25%. And again, just the null hypothesis is true, so we are looking at the percentage of tests that would conclude that the alternative, or that we would reject the null hypothesis. So in this case, it would be the same as the p-value cutoff. Okay. Number 5. In a population, 85% of the people are in class A, and the remaining 15% are in class B. So 85% are in A, 15% are in B. For people in class A, a classifier has an accuracy of 90%. For people in class B, so out of our population, we're splitting into these two, and then we're splitting these into accurate and not accurate. Okay, so in class B, the accuracy of the classifier is 98%. And 92% not accurate. One person is picked at random from the population. What is the chance that this person is classified correctly? So if we look at this diagram that I drew here, the people that are going to be classified correctly out of the population are the ones with the accurate descriptions. So that's going to be 0.85 times 0.9 to get this percentage, and then we're going to add that to 0.15 times 0.98 to get, Okay, yeah, we want to add that to 0.98 to get this percentage. So that is the chance of the correct classification. Okay, now if we look at part B, it says, given that the person is classified correctly, what is the chance that the person is in class B? So, to find this, we want to look at the chance that the person is in class B given that they are classified correctly. So, we can see that this is their likelihood that someone will be classified correctly given that they are in class B, and then we want to look at everyone that's classified correctly at all. Okay. Alright, this question is a little bit tedious because you have to draw a graph, but let's just jump into it. Okay, so a new function that takes a numerical argument is defined as follows. So this function takes in an argument c. If c is less than -2, it returns 4. If it's greater than 2, it returns 4. And, else, so basically if it's in between -2 and 2, we're going to return abs of c plus 2. Alright, so we want to draw the plot generated by the following code. Just ignore the labels on the axes, and yeah. Okay, so first thing we see is that we're making this table called T. So I'm going to just go ahead and draw out really quickly what T would look like, because that's generally what I do when I see that a question has a table in it. Alright, so T has this column X, which has NP range -3, 3.1, and 1. So that's going to be 3, or -3, -2, -1, 0, 1, 2, 3. Alright, and now we see this next column, this next table, is T with a column Y. So we're going to add this column T, Y, to our table, and we want to use this function applied to X. So we are going to basically look at all the X points and apply the function. So starting with -3. -3 is less than -2, so this is going to return 4. Now we go to -2. -2 is going to be in the else statement, so we want to return abs of -2, which is going to be 2 plus 2, so that's 4 as well. -1, again, is the else statement, so we're going to return abs of -1, which is 1, plus 2, which is 3. 0, that's just going to be 2. 1 is going to be 3. 2 is going to be in the else statement as well, so that's 4. And 3, we are finally in this elif statement, because 3 is greater than 2, so we're just going to return 4. Alright. And this is just going to be a scatter plot, so let's go ahead and draw approximately what this plot would look like. So here is Y, this is X, 1, 2, 1, 2, 3. Okay, so we have -3, 4, which will be up here, -2, 4, which will also be up there, -1, 3, and so on and so forth. Okay, so that is basically a very messy version of what this scatter plot should look like. Alright, so we go to the next question, and it says, let's say we did minimize on the function. Alright, so this is our function, and what is it going to evaluate to? So we drew this graph, and as you can imagine, if you're going to be looking at numbers that are greater than what we have here or less than, they're always going to be 4, because in that case, c is going to be greater than 2 or less than -2. So this is basically all we have to work with for minimize. And if we look here, at this point where we have x equals 0, this is the minimum value of the function because it's just returning 2, which is smaller than 3 or 4, which are all the other values returned by this function. So our answer is actually going to be 0, which I think is a little bit confusing because it's going to be returning the minimum value of 2, but minimize is going to actually give us 0 because that's the argument that we pass into the function to get this minimum value. So basically I already explained that, but an output of 2 at c equals 0 is the minimum output for this function. Okay. Alright, so moving on to number 7. So we have a hospital system that has data on the systolic and diastolic blood pressures. I probably pronounced that wrong, but it's okay. Both measured in millimeters of mercury of hundreds of thousands of patients. Assume that it's roughly football-shaped with an unknown correlation coefficient R. The table BP consists of one row for each of the 300 patients, sampled at random from the population of patients. It has 2 columns, so I'm just going to draw out really quickly what this would look like. So it has column systolic and diastolic, which has all the information for 300 patients. Okay. So complete the code below so that the last line evaluates to an array consisting of the endpoints of an approximate 90% bootstrap confidence interval for R, based on 10,000 repetitions of the bootstrap process. You may use a function core that takes as its arguments 2 numerical arrays of the same length and returns a correlation between them. You do not need to define a core, so we just assume that we already have core. Alright, so basically when we look at this, we see that it's going to be set up the same way that any sort of bootstrap confidence interval is set up. So it starts out with this array that's being made called R values. So for I in NP range, and we see up here in the question that it wants 10,000 repetitions, so we want to do 10,000. Oops. Okay, 10,000. Alright. And we want to do something to resample from this table. Since we know it's a table, we are just going to do dot sample. Okay. And new R, as we saw up here, core is going to be taking in 2 arrays as its arguments, and it's going to just be finding the correlation between those 2 arrays. So we want to be looking at resample, which is the new table, which is resampling this table BP, and we want to be looking at the 2 columns because those are arrays. And we want to find the correlation between the systolic and diastolic blood pressures. So we can look at column 0 and 1. Or, if you want to write it out, just systolic and diastolic. Alright, and then 2 R values, we want to append the new R. So we will just do np.append r values and new r. Okay, so now we're looking at the confidence interval, and we're looking for a 90% bootstrap confidence interval. So on either end of that is going to be 5%, since we're looking for 10% off the entire thing. So percentile 5 for the left end, R values, and 95 for the right side. And we want to finally be returning left end and the right end. Okay. So how will we use this interval to test whether or not r equals 0.6? And your answers should include the cutoff for the p-value. So we are using a 10% cutoff for the p-value, since the bootstrap confidence interval is 90%. Keep doing that. Okay. 10% cutoff for the p-value. And basically what we want to be doing is looking to see if 0.6 is included in this confidence interval. And if it is, that means that we can reject the null hypothesis and say that 0.6 is included in the confidence interval. And if not, we can... Wait, sorry. Okay, if it is in the confidence interval, we can't reject the null hypothesis. And if it's not, that means that we can reject the null hypothesis by saying that it's not in the interval. And that is going to be with a 10% cutoff. Okay. So now we're moving on to number 8. So the prices of 152 cars are summarized in the table below. Prices are in thousands of dollars. Each interval includes the left endpoint, but not the right. So the first thing I do when I see something with intervals like this is I normally write out what the intervals are, because it just helps me to visualize things better and like understand what the graph is going to look like, or the histogram. So for this first interval it's 12, for this one it's 5, this one is 7, this one's going to be 6 plus 6 is 12, this one's going to be 8 plus 4, so that's also 12, this one's going to be 12 again, and this last one's a big one, it's 40. Okay, so we can also see the number of cars in each of these: 26, 26, 30, 29, 14, 14, 13. So something that I noticed right off the bat is that these two numbers are the same. These two are also the same. But in this case, the intervals are different, so we're going to be seeing different heights for those. So immediately, I am going to be looking at these histogram options, and the first one that I see and can immediately just get rid of is going to be number 3, because I see that even though these intervals are very different and they have the same number of cars, they're almost like exactly the same height, so I know that's obviously not going to be the right answer. And then once I look at 1 and 2, I see that in number 1, even though the first interval is more than twice times the second interval, and it has the same number of cars, it's very close to the same height. So we can also cross it off immediately and conclude that number 2 is the histogram. And we can tell that just by looking at these first 2 bars. Okay, now if we go to part B, so it says, the prices are sorted in increase in order and placed in the array prices. Thus the expression length prices evaluates to 152, so there are 152 prices in this array. Here are the first 20 entries, and it's just a bunch of prices given to us. So it says, what does the following expression evaluate to and why? Percentile 10 prices. So it's going to be giving us whatever the smallest entry is that corresponds to at least 10%. So immediately we're going to find what 10% of 152 would be. So, so we can just do 0.1. Okay, so that would be 2, 5, 1. So we want to be looking for something that is at least 15.2 entries into this array. So that means we're going to be looking for the 16th entry, since the 15th entry is not at least 15.2. So 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 10, 11, 12, 13, 14, 15, 16. So this is going to be the entry that we choose. And this is what it's going to evaluate to 19.08. Because we're looking for the percentile, which is the smallest entry that is at least 10% of the array. Okay, so number 9, we see researchers studying health insurance in the United States have gathered data on whether or not people are insured. There are several thousand people in the study. The table insured contains one row for each person. It has 3 columns: name, zip code, and insured, which has a variable with either 1 or 0, where 1 means insured and 0 means not insured. Okay, and then we have another table called states, which I'm going to write up here because this is going to take up a lot of room. And it has 1 row for each zip code in the United States. The first column is zip code. Second column is state. Okay. So, write Python code. You can use multiple lines of code. Last line of your code evaluates the element described in the question. So, for this first question, we want to see the proportion of insured people in the study. So, what we want is the number of people insured divided by the total number of people. So to get the number of people that are insured, what we want to do is we want to take this column and take the sum of it, because if we do that, we're going to be getting all the insured people because they have a value of 1, and we're just going to be adding those up. And the people who aren't insured, because they have a value of 0, aren't going to contribute to this. So what we want to do is sum of insured column 0, 1, 2. And then we want to divide that by the total number of people in the study, which would be insured numbers. Okay, so that's part A. Now we look at part B, which says we want to find the state that has the largest number of insured people among all the states represented in the study. So immediately we can see that insured doesn't even have the states in it. So we're going to want to be joining insured with states so that we can get the states for all the people in the insured table, because we already have the zip code, we just need to get the states. So the first thing that I did when I was doing this problem is I made a table with these 2 tables joined, and I called it with states. So we want to do insured dot join zip code, which is the name of the column that we want to join for the 2, and we want to be joining that with states. Okay. So the next thing I did is I grouped this table by the state, because we want to be just looking at the individual states. Alright, so I'm going to make that into a new table called grouped equals with states dot group, and we want to be grouping by state. Oops. And Also, when we use group, there's a optional second argument, which is how you want the data to basically be aggregated. So in this case, when we are grouping this table, we want to be finding like the total number of people insured, so we're also going to want to do sum like we did in part A. Okay, and now that we have this table, which is grouped by the states, we want to be looking at the states that have the most people insured. So we want to do sort by insured sum. Sorry for my horrible handwriting. Okay, so insured sum is going to be this column with everything summed up based on the state. Oh, and we also want to make sure that's descending since we're looking for the biggest one. And now we just want to be taking the largest, the first item, or sorry, we want to be looking at the first row because that is going to be the state with the largest number of people insured since we sort of by descending order, and we want to be looking at the state. So we're looking at column state, and then item 0. Alright, and now we've gotten to part C, which is a state that has the largest proportion of insured people among all the states represented in the study. So this is really similar to the one that we just did, but we want to be looking at proportion instead of just the number. So we want to do something very similar to what we just did. So what I did is I did something similar to the grouped table, except we're going to be doing something slightly different. So I called mine group count. So I did use with states from the previous number, so we're just going to go ahead and draw that arrow there so we are sure we know what we're doing. Okay, so we grouped with states the same way that we did before. So we grouped that by state. We actually don't want to be doing the sum this time. Because we want to have those numbers still intact. Yeah, so we want to have just the count of people, just the count of, okay, so what we just did is we grouped the table by the state, and that's going to group everything by the count, but we also want to be using the sum from the previous question, because we want to be dividing the sum by the count. So we want to add the column, insured sum from our previous table. Wait. Okay, now we want to get a table with the proportions. So what I did is I just made a column called proportion, or a table called proportion. So in this table we're going to take grouped count, and we're going to just add a column to it that has a proportion. Oh man. Okay, grouped count with column. We're just going to call it prop, and that's going to have grouped count column, and we want to divide the sum by the count, so we do insured count, which was made when we grouped everything, We want to divide that by grouped count column insured. Oh, whoops, my bad. This should be the opposite. Okay, so we want to divide the column insured sum by the column insured count. Okay, and then we want to sort that because now we have the proportion where we want to be looking at the biggest proportion. So we want to sort that by prop, and we want to do descending equals true again. Okay, and now we want to be looking and doing basically the same thing that we did up here, where we were finding the biggest proportion and then taking that state. So we want to do, proportion is the name of the table, dot column state, and since we've already sorted it, we just want to do item 0. Alright, so that is part C. Alright, moving on to number 10. Alright, so a population consists of more than 500,000 people. Histogram A is an empirical histogram of the mean weight of a random sample of 100 people drawn with replacement from the population based on 25,000 repetitions of the sampling process. Histogram B, blah blah blah, of the mean weight, so these are both of the mean weight of a random sample drawn with replacement from the population, also based on 25,000 repetitions, but the sample size is unknown. So in here we have a sample size 100, here we don't know the sample size. Okay, so the first question is asking about the SD of this first histogram, and since this is a normal distribution, we can basically just look at the histogram and kind of estimate what it's going to be. So if we look at this distribution, we see that it changes concavity around here. So that's going to be like where the labels are. So the SD appears to be about 2. We actually can do this for the next one as well, because it's also a normal distribution, so we see the SD is about 1 on this one. Alright, so the SD of the 25,000 sample means used to construct histogram A is closest to, and in this case, we can just say 2 pounds because we've looked at the histogram, we see that it changes concavity here. And since it's a normal distribution, we can basically just look at it. Also, based on the central limit theorem, more than 90% of the data should be within 3 standard deviations of the mean. If we look at 3 standard deviations, we see that basically has all the data, so that just basically is a sanity check that shows us that we're doing things right. Alright, so let's look at part B. The size of each of the 25,000 sample means whose means were used to construct histogram B is closest to blank. And immediately we don't know this because we don't know the sample size, it wasn't given. But we can use a formula that we already have to solve for it. So we know the standard deviation of this first sample, and or of the sample mean, I mean, and we can use that formula from the central limit theorem to solve for the population SD, which we can then use to solve for the sample size for the next histogram. So that sounds really confusing, but let's just go ahead and start doing it. Okay, So the SD of the sample mean is equal to the population SD over the square root of the sample size. So in the case of number 1, we already know the SD of the sample mean, which is 2. We don't know the population SD, but that's what we're solving for. And we know the sample size is 100, so square root of 100 is going to be 10. So 2 equals pop SD over 10. So the population SD is equal to 20. Alright, and once we have that, we can use that to solve for the sample size of the second histogram. So, we know that the SD of the sample mean in this histogram is about 1, because we basically can just see that looking at the distribution. So we're going to do 1 equals pop SD, which is 20, over square root of the sample size. Alright, so then we know that the square root of the sample size is equal to 20, and square both sides, and we know that the sample size is 400. So the answer is 3. And basically you can just explain how you solved this or show your work, and that's basically an explanation. Alright, moving on to number 11. Alright, so the plot on the right shows 15 points along with a regression line. The data represents thousands of women in the United States, grouped by height to the nearest inch. For example, all the women whose heights are 62 inches to the nearest inch form one group. So basically we're going to be taking a lot of data and just aggregating it into a bunch of points. The value on the horizontal axis is the height to the nearest inch. The value on the vertical axis is the average weight of women in the corresponding group. Correlation is about 0.995. So, in part A, it's asking us to look for the residual plot, and we basically want to be looking at this graph. And immediately something that I noticed was that I could see that this data is kind of forming a pattern in which it's not exactly matching up with the regression line. It's actually going to be going kind of like this. So it's forming this curve where it starts above the regression line, goes below it, and goes back above. So, if we look at part A, which of the graphs goes best with this? It's going to be the first one. Because in this graph, the data starts above the regression line, goes below it, and then comes back above. And basically, it just looks like the data compared to the regression line. Oops. Data compared to regression line. Again, if you look at this plot, you can basically just see that the data is following the same pattern, which we will see in our residual plot. Okay, so now moving on to part B. If you draw a scatter plot consisting of 1 point for each of the thousands of women, with her height on the horizontal axis and her weight on the vertical, which is going to be basically the same thing as this, but instead of doing the average weight, we're going to have a point for every woman. Will your scatter show a correlation of about 0.995, which is the same correlation that we have in this one, more than or less than 0.95. Pick one option and explain with reference to the scatter plot of heights to the nearest inch and average weights given in this problem. So, the difference between what we have right now and what we are predicting is that with this plot, we're looking at the average weight. So we're taking all these women that identify or that are this height, and we're going to be averaging out their weight and putting it into the data. Versus with this graph that we would be looking at in part B, we would have each of the individual women. So we'd have like a lot of different points all around this regression line. So basically, if you think about it, the correlation is going to be less than 0.95 just because there's going to be a lot more points. They're probably going to be further from the regression line. There's going to be a lot more outliers. It's just not going to be like as close of a fit. Because in this case, with the averages, it's basically going to normalize a lot of the data, so it's going to be more centered around the line since we're just taking the average as opposed to looking at every single point. Alright. Moving on to number 12. So in a large random sample of U.S. households, the median annual income is $54,000. The original sample is bootstrapped 5,000 times, and the sample median is recorded for each of the bootstrap samples. The middle 95% of these intervals is 53,000 to 55,000. Alright, so the first question, we are just looking at true or false, and it says the interval 53,000 to 55,000 is an approximate bootstrap 95% confidence interval for the median income of all the households in the sample. So, when I immediately looked at this, I thought that the answer was true, and that's actually what I ended up putting. But if you look at what I underlined here, it says that it's a bootstrap confidence interval for the median income of all the households in this sample. And that's actually not correct, because this is going to be a bootstrap confidence interval for the median income of all the houses in the population. So that is basically the answer to that question. Okay, so B is pick the option that you think best completes the sentence and explain your choice. Alright, so it says, the percent of all U.S. households with annual income in the range of 53,000 to 55,000, either 1 is about 95%, 2 is about 50%, or 3 cannot be approximated based on the information given. So, this is actually just going to be a bootstrap confidence interval for the median income of the population. So it doesn't actually tell us anything about the percent of U.S. households in this range. It doesn't really correlate, or it doesn't really relate to what we're looking for at all. So that doesn't tell us anything. So this is going to be the 95%, confidence interval for median of population. Okay. Part C says, if you calculate the mean of each of the 5,000 bootstrap samples and take the middle 95% interval of the 5,000 means, the center of the new interval will be less than 54,000, about 54,000, or more than it. So, something that we went over when I took the class was that the reason that we usually are looking at the median income is because, as opposed to the mean income, is that the median income isn't going to be skewed the way the mean income is, because when we look at household incomes, it's probably going to include a lot of really high incomes, and that's going to skew the data and give it a really big right-end tail. So if we're looking at the mean, actually, it's going to be probably more than 54,000, just because means will tend to have a long right-end tail, which are going to skew it upward in terms of household incomes. Mean Alright, moving on to number 13. So, the handedness of a person refers to whether the person mainly uses their right hand or left hand. Some people are ambidextrous. In a study of whether handedness is related to gender, a random sample of 1,000 people was taken in a country. There are 488 men and 512 women in the sample. Distributions came out as follows. So, here we see there are more right-handed females, more left-handed males, ambidextrous, there were more males. And part A, to test whether or not handedness and gender are related, we did null and alternative hypotheses. Does the null hypothesis say that the two distributions above are the same? If not, which two distributions does it compare, and what does it say about them? So actually, in this case, the null hypothesis is not going to be saying that they're the same. So, oops. Okay, so the answer to that is no, because we are looking at actually the underlying distributions and comparing if those are the same. because if they were the same, any changes from the actual model in terms of gender are just going to be due to random chance. And we're looking at that distribution as opposed to looking at these two distributions and saying they're the same. Okay. So the alternative hypothesis is basically just going to be something opposite, which is that the two distributions are not drawn from the same underlying distribution. Or, in other words, handedness and gender do have something to do with each other. Same underlying distribution. Alright, so when we think about the test statistic, immediately what I thought of is total variation distance, because we have these two arrays, and we want to be looking at, like, the differences between them. So, that's a great choice for a test statistic because it's showing the difference between two distributions. So, test total variation distance. We're not actually going to do the entire calculation, but I'm just going to write out what it would be. So we're taking the absolute value of the differences between these two. So this would be 0.75 minus 0.875, I mean, 0.95 plus, oops. And all of that divided by 2. And again, that's just because that's what total variation distance is. Alright, so to carry out the test, the process starts with one of the following. So it's either 1, drawing 512 times at random with replacement from the distribution of males in the table above. So let's just think about this. This obviously doesn't make sense because there were only 488 men in the study versus 512 women. So there's no reason that we would be doing this, even if this was correct, we would be doing 488 men. We would do 488 draws. So that's not correct, and clearly number 2 is not correct either. So that leaves us with what is the correct option, which is permutating all 1,000 people and labeling the first 488 male and the remaining 512 female. And the reason we're doing this is because we want to find out if this underlying distribution is the same. So we want to look at all of the people that we surveyed, and we want to basically act as if they have, a randomly assigned gender, and if we get, similar distributions to this, or at least not ridiculously far, then we can say that yes, these probably do come from the same underlying distribution. So basically that's just going to be telling us what we conclude. So the goal is to see if underlying distribution is equal. Alright. So we move on to number 14. We're almost there, just a couple more. Alright, so this code below generates a plot. So we have this table called data, which I'm just going to draw out really quick. So it has columns x and y with this array -1, 2, and 0 for x, 2, -4, and 0 for y. And then we have this function called MSE, which we can assume is mean squared error, and it takes in this argument slope. It sets intercept equal to 0. It computes predictions, which is slope times data column x plus intercept, and then it returns the mean of predictions minus data column y squared. So we've seen something like this before. It's basically just going to be finding the minimum squared, or the mean squared error. And yeah, that's pretty familiar, not too difficult to figure out. So MSEs equals slope, apply MSE potential slope. Oh, I totally missed the line. Okay, so slopes is a table with the column potential slope. And that has a range from -3 to 1. So -3, -2, -1, 0. And we want to apply this function MSE to these potential slopes. And then we want to add it to a column with the MSEs. Yeah, so we're basically just finding the mean squared errors for each of these potential slopes. And when I did this, I actually took a long time calculating out every MSE, so I'm probably just going to calculate out one and then give you guys the rest of them. So let's do the mean squared error for -3. So, the potential slope that we're putting into MSE is -3. So we look in here and we see intercept is 0. Predictions is going to be the slope, which is -3, times data column x plus intercept, which is 0. So -3 times -1 is 3. -3 times 2 is -6. -3 times 0 is 0. So then we're going to return the mean of, okay, let's just start by doing predictions minus data column y. And then we're going to square those and take the mean. Okay, so 3 minus -1 is 4. -6, or wait, that's wrong. Okay. 3 minus 2 is 1. -6 minus -4 is -2. 0 minus 0 is 0. So then we're going to square those. So this is going to be 2, this is going to be 4, this is going to be 0. And we're going to take the mean of that. So 2 plus 4 is 6, and we're going to be dividing by 3 because that's the total number. So that's going to have, oh, I messed up. When we square 1, we're going to get 1, 4, and 0. So we're going to get 5/3 for the mean. Alright, so that's the mean squared error for this one. I'm just going to go ahead and write out the rest of the mean squared errors because it took me a while to calculate all of these, and I feel like it's kind of a waste of time. You guys can do it on your own as an exercise. So the mean squared error for -1 is 5/3, again. For -2, it's 0, and for 0, it's 20/3. So if we plot that out, so this is the potential slope, and this is the MSE. So for -3, it's going to be 5/3, which will be right above 2, or right below 2. So that's -3, 5/3. For -2, it'll be 0. -1, it'll be 5/3 again. And for 0, it'll be 20/3, so it'll be way up here. And that's basically what that question is asking for. Again, it's basically just going to be a scatter plot. I would write the names, or not the names, but the numbers for each of these points to make it more clear, but I think it's fine since I just told you guys what they are. So let's look at part B. So these are 4 equations for lines We're looking for the lowest mean squared error in predicting the y column based on the x column according to the plot we made. So if we look at this plot, the mean squared errors are 5 over 3, 0, 5 over 3, and 20 over 3, based on the slopes -3, -2, -1, and 0. So immediately we know the thing that has MSE of 0 is going to obviously be the best fit. So it's not going to be 1, not going to be 3, and not going to be 4. It's going to be 2, which has the slope of -2, since that has a 0 mean squared error. Alright. Moving on to number 15. So, we have a random sample of 1,000 12-year-olds who took a test, a multiple choice test. One of the questions had 5 possible answers, one of which was correct. Test results showed that 180 of the 1,000 students got the question right. This alarmed some educators who said the kids did worse than they would have by random guessing. But other educators said the results were like random guessing, allowing for chance variation. Show how to perform a statistical test to see which educator's viewpoint is better supported by the data in the following steps. So, in this case, the null hypothesis would be that the kids did the same thing that they would have by randomly guessing, which is a 1/5 chance of getting the answer right, and any variation from this model is simply due to chance. Same as random guessing. One-fifth chance of correct. Variation is due to chance. Okay. And for the alternative hypothesis, we also want to keep in mind that the goal is to decide between the two viewpoints of the educators. So this alarmed some educators who said that they did worse. So we want to be looking and saying that they specifically did worse as opposed to doing, better or worse. So for the alternative hypothesis, we are going to be saying that they did worse. The kids did worse. Oops. Than the 1/5 model. So they had a less than 1/5 chance of getting the answers right. Alright. Part C. Suppose the test is performed using, as its test statistic, the number of students who get the answer right. Draw a sketch of the empirical distribution of this statistic under the null hypothesis. Mark the observed value of this test statistic in a reasonable place on the horizontal axis. So, since the test statistic is just going to be the number of students who get the answer right, we can basically just do what's going to be like a normal curve. Oops. So, at the center it should be about 1/5, so that's going to be 200 out of 1,000. Then here we're going to get like 220, 240, etc. So this will be 180, 160, and so forth. Okay. So the observed value of the statistic is 180, so that's in a fairly reasonable place. And then on the sketch above, shade the area corresponding to the p-value, and explain why you chose to shade that region. So the p-value is going to be the results in which the answer is more extreme than or equal to what was actually in the observed test statistic. So in the observed test statistic, 180 kids got the answer right, and anything more extreme is going to be less than 180, so it's going to be this area. Equal or more extreme. Wow. That voice crack. Okay, more extreme. Alright. So now we're on number 16, which is actually the last question. Okay, so bootstrapping is a way of replicating a sample so that you get a sample that is similar but most likely not exactly the same as the original sample. There's a chance that the bootstrap is exactly the same as the original. In this problem, you will find that chance. Alright, so the original sample consists of 4 people: John, Paul, George, and Gringo. This sample will be bootstrapped. Find the chance that all 4 people appear in the bootstrap sample. Your answer will be just an arithmetic expression. So, when we look at this, we're going to think about what is the chance that the first person, that one person, any person from this distribution, are going to be in the sample. And obviously that's first probability is just going to be 1, because any of them can be chosen and that first person will be correct. And once we get the first person, let's say we get John, then we want to find the chance that we're going to get Paul, or, you know, any of the other 3 that we haven't already chosen. So the chance that we're going to get one of the other ones is going to be 3 to 4, because there's 3 people left that we could get that would still result in the correct combination. And then let's say we got George. Now there's only 2 out of 4 left that would be correct, so the next, well, we're going to multiply by 2 out of 4. And then finally, if we got Ringo, the chance of getting Paul, who is the last one we need to have exactly the same sample, is 1/4. And we're going to be multiplying because in this case we need to, okay, so in the case of like the first one, we got one of the members of the Beatles, and for the rest of the bootstrap sample to be exactly the same, we need to get one of the other members. So these things all need to happen, which is why we're going to be multiplying them instead of, say, adding them, which we would do if they were separate instances in which the sample could be correct. Alright, so let's move on to part B. So the original sample consists of n people. So in the example above, n would be equal to 4. So the sample would be bootstrapped. Write a Python function called same that takes n as its argument and returns the chance that all n people appear in the bootstrap sample. And it says there are many different ways of writing this code. Any correct way is fine. So we basically want to be doing something very similar to what we did above, where we want to write a function that's going to just generalize this idea. So we're going to start by just writing def same, and it's going to be taking in n as its argument. So, the way I thought about this is we're going to want to be going into a for loop and multiplying so that we can, and we want to, we always want to be decreasing this number in the numerator, because in this case, in this example at least, it starts out with 4/4, goes to 3/4, 2/4, and 1/4. And we're going to be doing a very similar thing with any n samples. So what I started out with is I defined something called fraction, which is going to be something that I'm going to change in the for loop. And I'm just going to define that as a fraction, which starts as 1. And we're going to just be multiplying that by different numbers as we go through. Alright, so we're going to go into the for loop. So let's do for I in np arrange n. So we want to actually be going through and multiplying by these different numbers over 4. Actually, we're going to make the range from 1 to n plus 1. So that will give us, oops, the correct fractions, because if we just did np arrange 1, or np arrange 1, n, we would have numbers from 0 up to n minus 1. And we actually want the numbers from 1 up to n plus 1, or n. We would want the numbers from 1 up to n. Like in this case, we have 1, 2, 3, 4. So, what I did here is I've defined a new variable called new fraction, very creative I know, and I set it equal to I over n. So n is going to be equal to the number of people, in this case it would be 4. I is going to be the number in the for loop, which in the first iteration is going to be 1, then it'll be 2, then it'll be 3, then it'll be 4 in this case. Okay, and we want to multiply this fraction by the new fraction, and we want to just be storing that in this variable that we defined outside of the for loop. So fraction is equal to fraction times new fraction. Oops. New fraction. So although this is a little bit different from what you've done before, it's really similar to the kind of bootstrap confidence intervals. Just instead of defining an array outside of the function, we're going to be defining a variable and then changing it inside or outside of the for loop, and then we're going to be changing it inside the for loop. And at the end, we just want to return fraction, and we do that outside of the for loop so it doesn't return too early. All right, so that is the entire exam. I hope you guys enjoyed this video. It's a wild ride, and good luck on your final.